induction is the phenomena in which EMF is induced in a coil when magnetic flux associated with that coil changes. There are two types of inductions. First one is self-induction and the other is mutual induction. Now, we are going to discuss about self-induction. In self-induction, EMF is induced in a coil when current in that coil changes. We know that a current carrying coil produces magnetic flux around it. Consider a coil which carries current I and the magnetic flux associated with that coil is phi. When the current in the coil changes, the flux associated with the coil also changes as they are directly proportional. That means phi proportional to I or phi equal to Li, where L is a constant which is known as self-inductance or coefficient of self-induction. When current equal to 1 ampere, then phi equal to L. Therefore, self-inductance is numerically equal to the magnetic flux linked with a coil when unit current flows through it. When current in the coil changes, the flux associated with the coil also changes and an EMF is induced in it. According to Faraday's law of electromagnetic induction, the magnitude of induced EMF is the rate of change of magnetic flux associated with that coil, that is epsilon equal to d phi by dt. But we know that phi equal to Li. So, the expression of the induced EMF becomes epsilon equal to d by dt of Li. Since L is a constant, epsilon equal to L di by dt. When di by dt becomes unity, that is 1 ampere per second, induced EMF is equal to self-inductance. Therefore, self-inductance of a coil can be defined as the induced EMF set up in the coil due to a unit rate of change of current through it. Expression for the self-inductance of a solenoid. Consider a long solenoid of length L and radius R having n turns per unit length. If current I flows through it, then magnetic flux linked with the solenoid phi is the product of flux linked with each turn of the solenoid and the total number of turns n. That is, total flux phi equal to flux associated with each turn into n. Flux linked with each turn is the product of magnetic field produced by the solenoid B and area of each turn of the solenoid A. So, above expression becomes phi equal to BAN, but magnetic field produced by the solenoid B equal to mu 0 Ni and total number of the solenoid N equal to number of turns per unit length into total length. Thus, the above expression becomes phi equal to mu 0 Ni into A into NL, or phi equal to mu 0 N square IAL. We already know that phi equal to Li. While comparing above two equations, we get the expression of self-inductance, that is L equal to mu 0 N square AL. If the coil is wounded over a material of magnetic permeability mu m, then L equal to mu m N square AL. Since mu m is the product of mu 0 and mu r, L equal to mu 0 mu r N square AL. Now, we are going to discuss about the factors on which self-inductance depends. The first one is number of turns. Self-inductance increases with increase in the number of turns of the solenoid. Second one is area of cross section. Larger the area of cross section of the solenoid, larger is the self-inductance. The third one is permeability of the core material. The self-inductance of the solenoid increases with the permeability of the core material.